Alright, we've got one more example from chapter 9. This really helps with most of the homework. The painters on this board, they stand on a board, they paint the building or the sign, etc. Well, the board stays level because of tensions in the wires, and the painters, they can't all crowd at one end, right? That will really flip it, but just by adjusting tensions and everything, the wires just keep it stable, and it works. So we can do a fairly easy physics problem, but as you go on, as you go through the homework too, like number 6 and 15 and 20, these will start to have more and more terms. Okay, and in the lab, we're going to go up to 6 things producing or not producing torque. Okay, so they stand on a uniform scaffold. The scaffold itself weighs 400 newtons. Okay, I'll try mostly to stay out of the way so you can see. Whoops, yep, that. The scaffold weighs 400, and naturally, so the scaffold is a metal scaffold. Its center of mass will be exactly at the center. So you can apply the weight right at the center. Good. Painter A weighs 1,000 newtons. And he's 1 meter from the left end of the wire. So we have 1,000, or from the left wire. And we need to have that's 1 meter gap. Okay. Painter B weighs only 600 newtons and is 1 meter from the right end. And the whole length, okay, so this picture is disproportionate. So that's 600 newtons, that's 1 meter, and these gaps that look much bigger, they are only 1 meter each also, because the whole scaffold is only 4 meters across. Best graphics I could find. Okay, so your problems are kind of sketched there for you, but I expect you to have like drawn all over them and maybe calculated on a scratch piece of paper. Or you could redraw the whole problem, if that helps. Okay, if the system remains in equilibrium, find the tension in the cords. Oh no. What should we even do? What axis would it rotate around? Okay. What? Are we still right? Oh, sure. Okay. Well, we certainly can. The sum of all the x forces equals 0, but we're not like swinging back inside to the pendulum or anything. What's even better would be to say the sum of all the y forces equals 0. Excellent. X and y. Okay, let's consider that. I'll give you 1 more minute to finish drawing the picture and writing things down. This is typed portion is part of the notes online too. So if you're completely lost. Okay. So to be really clear, I would write some of the y forces or even y net or anything like that. I have to do plus the tension in the left wire plus the tension in the right wire. Why are those plus as opposed to minus? Sure. Exactly. I'm on the y-axis and they're pointed up. Okay, minus 1,000, 1,000. Minus 400. I already marked these as forces, so I don't need to worry too much about units. Hey, that's nice that they add up to 2,002. So minus 2,000 newtons for the 2 painters plus the scaffold equals 0. Uh-oh. Yeah, we have 2 unknowns. That helps some. It's good to have that rule. We're going to need it, but that doesn't solve the problem. Just saying I have 2 tensions. I have tensions on each side. They're probably not equal because the way heavier guy is over on the left, the lighter guy's on the right. So I could guess right away that they're not equal. It probably takes more tension to hold this side up, but the problem's not over. What else has to add up to 0? Oh my, okay. We just vaguely talked about it Thursday. Hopefully you were focused on the test. But so I have a meter stick on my desk here, and it's got some weights on it. And it doesn't accelerate up or down or anything if I let go, but it will twist. Like one side rotates over. And so if these guys are going to not flip over and roll their scaffold off the side of the building, we also have to have the torques equal to 0. The twisting forces here, and I actually want the picture there. We use this weird curvy T. The sum of all the torques has to be 0. And torque is R perpendicular times the force. And if there's an angle other than 90 between them, I have to take the sine. What was this R with a perpendicular sign? It had a special name that belongs in your notes for the notes check Wednesday. Sure landed. It's called the lever arm. The lever arm has to be measured from an axis. And where do we pick the axis? Should I do some complicated averages problem and calculate the center of mass of this system with the guys in the scaffold is at the center, and the guys are each 1 meter from the center? We can figure it out. Let's not do that. Any axis will work. Don't believe me? Let's try the left end of the beam. Okay. Let's do the torque for each one of these things. 0 times TL. It hits right on the axis. It has no lever arm. Okay. By physics silly convention, counterclockwise torques are positive because positive angles go counter. I'm making the wrong thing backwards to the class, but counterclockwise angles are positive on the math axis. We're addicted to math and physics. So all these weights are negative. So I do minus 1,000 times 1. Oh, sure. Nice one. Minus 400 times 2. Because I'm now 2 meters out from the axis. And minus 600 times 3. Wait a minute. That all can't equal 0. Should make my dots bigger. What am I missing? There's one more tension. Excellent. Plus tension in the right wire times 4. So it has a longer lever arm. That right wire has got to apply enough force to counteract all the downward twisting of all 3 of those forces. Okay. I'm going to scroll up and calculate. Okay. So 4 times tension in the right wire equals 1,800. Let's move that. 1,800. So 1,000. Is that 3,600? 800 plus 18 is 26? Yeah, I think so. So 900 newtons in the right wire seems reasonable. And the left one, okay, if that was 2,000, the left one must be 1,100. Because they had to, from the first equation, they had to add up to 2,000. Okay, seems reasonable. The 2,000 newtons from each wire supports the total weight of all the guys plus the scaffold. The left one is more, even though I calculated that later, because the heavier person is closer to there. Makes sense. It's alright, make sure you have that first solution down. And you could repeat that, yeah. Yes, if the two people were equally spaced from the center and they both had the same weight, then you would expect both cables to have the same. Okay, but we can try that in the lab. Those are boring problems. Okay, and you can see, so okay, in question 6 and 15 and stuff, they're all over the place, and they're all different values. Okay, but it's just the same procedure. You have to you have to space it out. And okay, scroll, scroll, scroll. Yes. Okay, real quick, just for me, there's our question. There's our start with the y forces. Okay, it's almost always y because gravity plays a big role. What if I chose the axis in the middle? What would my torques be? The sum of all the torques, whoops, taus, for torques. Okay. Oh man. So now I have, the 400 doesn't count. I have negative torque minus 400 times 1. Sorry, I keep flipping which out of my own habit. Where's the distance and where's the force? But it's force times distance. So not making joules, by the way. Oh, it's 600 for the man. 600 for the painter. I have plus TR times 2. Okay. I have, oh man, plus, yeah, I have plus 1,000 times 1. That looks complicated. And minus TL times 2 equals 0. Okay. So at first, this looks kind of bonkers. Okay. But if I do this subtraction and divide by 2, I get the math that TR minus TL equals, oh no, because I have to subtract this over there. Sure, equals minus 200. Okay. Or you could write TL minus TR is plus 200. The difference in the tensions is 200, and they add up to 2,000. Well, what numbers have a difference of 200 and add up to 2,000? It's only 900 and 1100. So even if I moved the axis to some weird spot that's not very convenient, it will still work. You can still do the math from any axis. You're just making it more complicated. So when you try these problems, and you can double check, this is what's hard. Well, basically, Chapter 9 is fun. We spend the rest of the week learning where do we put the axis. You put it on one of the unknown values. So you get to multiply that one by 0, and you get the simplest possible, because its lever arm will now be 0, you get the simplest possible equation for your torque result. Okay, that's the trick. And you always balance out the forces. Don't worry, it's not left out. It's still one of the terms in the force equation. But so you set that torque, you use your freedom of choice of axis to make one of those 0, and then you get something nice to plug in. So in the green it was not so nice, but in blue it worked out really nice. Okay, something easy to plug in for what you're left with. Any questions? Okay. Yep. So some fairly easy and fun math. Here, pause, stop that.